Hello viewers and welcome to a new STM32 World Tutorial video. In this video we are going to develop a custom bootloader and an application running under that custom bootloader. In an earlier video, see on the screen right now, number 22, we illustrated how you could software-wise jump to the built-in bootloader in an STM32. But the built-in bootloader, well, it can do one thing, it can flash. We might want a bootloader that can do something else, like, for example, verifying the signature of a new firmware version and roll back to the earlier version if the new one doesn't work. There's a lot of things you can do. We're not going to dig into that, but we are going to try to develop our own DFU, device firmware update, USB protocol bootloader today. So stick around to the end. To be honest, I don't know how long this video is going to be right now. As usual, I'm not scripting this. I am improvising as I go along. I also don't know if this is going to be one video. I suspect I might need 2 or even perhaps 3 videos to get through this topic in a reasonable manner. I'll try to keep this well below 1 hour video. That's my goal anyway. Now, if we look at our first Black Pill Blink application here, we can see that the Black Pill boards have 512 kilobyte of memory. Now, the problem if you want to do a DFU device firmware update over USB, you can't overwrite the code that you're currently executing. That's simply not possible. So you need to split this up in a separate firmware that will not be the bootloader, which is not going to be updated, and the application in another region that will be updated. So without further ado, and I am going to do this step by step from scratch, let's get cracking and let's try. No, I should start by saying that one of the first decisions you have to make is how you want to split up the memory. Do you want to put the bootloader at the start location 800 and then jump to the application, or do you want to put the application first and then somehow inside the application jump to the bootloader, which you then place on a higher address in memory? Both approaches are definitely possible. We are going to take the first approach. We're going to put the bootloader first, and then we are going to put the application at a later address. So without further ado, let's get started. So I am going to create a new STM32 project. Yeah, I should probably have done this before so that these were up to date. My internet is not the fastest in the world, or STM's website is not the fastest in the world, what do I know? So it usually takes a little bit of time the first time I'm doing it. How many does it need to get? Okay, not too bad. So target selector, initializing, so we are going to use the STM32F411CE U6 actually, so it is that one. So we are going to create 2 projects. So we are going to do the Black Pill bootloader and finish. Again, the first time it's usually a bit slow, but it will speed up when we do it later. There we go, I think. So let's do the basic configuration while we are in here. First of all, in sys, we are going to, well, we can enable all of it. I'm not going to use the trace actually, but let's also set it to crystal, and I am also going immediately to go down under connectivity and enable my USB device only mode. I'm not going to do anything, and then let's go into the clock. The reason I'm doing this is that these guys are running on a 25 megahertz crystal, and normally you would run it at 100 megahertz internally, but that you cannot derive the 48 megahertz clock from that. So I think if we set this to 96, it should be able to resolve 96. So we can do our 48 megahertz DFU clock. It's here. And run at 96. So 96, 25 megahertz is working, and now we can go in and we could also, let's right away go down. First of all, let's enable our UART asynchronous mode. As usual, I'll run 2 million BPS, which works for me. And then I'll go down on the middleware and USB device. I will enable the device firmware update. I'm not going to do anything right now, but let's try to generate the code for this one. So that enable code, and let's try to project. Let's try to build the project straight away because I want to see how big it gets. And we will see that, as usual, it doesn't load first time. Okay, I'll get back to that, but let's try to create another project because, as I said, we need two. So we will do the same processor. If 411 CEU6 there, and we will call this one Black Pill Bootloader application. Okay. So let's go through the same settings I did before. I will enable this. I will go in and I will set a crystal. I will go to the clock configuration, 96. I should probably have enabled the USB first because it's going to complain now. So let's go to the connectivity UART, asynchronous 2.0.0.0.0.0 and USB device only. Did that? Oh, that actually worked without complaining because I set it to 96 already. And let's go down under USB, under middleware, USB device, and we will set it to something else. We could set it to a virtual COM port, for example. It doesn't really matter in this case, as long as it's different from the other one. Let's close this one. Generate code. So now we have two applications that both built, and we have the bootloader and we have the bootloader application. So let's go back to the bootloader and let's check how big that actually gets. So if we go into source main, we can see down here that it is actually 29 kilobyte of memory, but this is unoptimized. So if we go into the project properties and we enable the optimization, which is here, we'll just optimize for debug, that's fine. And let's try to build the project again. It should shrink significantly, 17 kilobyte. So we could not fit this in. We could fit this into 32 kilobyte of memory, but let's actually make it a little bit bigger than that. So the first thing we want to do is to implement a little bit of functionality in our bootloader. So let's go into our, we need to, as usual, do our, I'm looking in another window, I'm sorry about that. So let's start by enabling our print redirect. So we will do a write function up here. We will also print out a statement on start. This is the bootloader, right? I am editing the bootloader, so printf a few empty line. So this should print out. Let's also implement our usual let's blink the LED. So we will set 32t now equals 0. Next tick, let's print out the tick and let's blink 500, and next tick 1000. That is basically all we usually do, and we will set now equals UV tick if now is greater than or equals 500. We will I actually didn't enable the LED, so let's do that actually. Let's enable the LED. So we go into our CubeMX again. There we go. And let's set this one to GPIO output. Let's call it LED. Let's go into the configuration of that GPIO and say we want that to be default high, so the LED is off, and we want to make it open drain. That should give us a blinking LED. So let's generate, or a LED we can blink. So now we can do a HAL GPIO toggle LED port and LED pin, and we can set our next, this was stupid, next blink, and we can set our next blink equals now plus 500. So that should enable the blinking LED. And let's do a now greater and equals next tick. Printf tick now divided by 1000. So we'll just count seconds. Next tick equals now plus 1000. Now let's try to run that. First time we're running this. I'm not okay. I could enable the serial wire viewer since I had that enabled in the MCU. And as usual, I have a printout put down here, and it should print out starting. So I'm going to make one change here, which I think will be necessary later. Let's say rather than starting, let's just write bootloader. So I need a few more of those to make it look decent. Let's try that. So now we have our bootloader starting. Now the bootloader itself is, as you can see right now, about 17 kilobyte, but let's allocate 64 kilobyte for this. So we need to go in and edit the linker script, which we have here. And we can see up here in the beginning, we have the RAM defined, we have the flash defined, and we have that at, so origin is that, but if we set the size rather than 512, we set that to 64K, and we try to build the project again. You should see down here that the free will drop. Why did it actually become bigger? A bit of a mystery. I want to make one more change. If you look at the last video, you can see that I actually changed this a little bit. So I made something in here. So E stack equals underscore B flag, and call the B flag is this -4. The exercise here is to leave 4 bytes at the top of the memory where we can mess around with transferring some data between the bootloader and the application. So that is about it. So our flash is, length is 64, RAM is that, and 128. So let's build our project again. Let's go into the source. Right. Okay, now it's finally updated. So we can see we now have 64 kilobyte of memory, and we have used almost 22 kilobyte of that memory, but the rest is free. If we try to run this application now, let's try to do that again. It will still run perfectly normal. Now the application, this address is necessary, is important to understand, because we are now using, of the 512 kilobyte available, we're using 64 kilobyte for the bootloader. That leaves us 448 kilobyte, and our address should be 8001,000. That will be the starting address of the application. So let's go in and try to create our application as it should be. So we close all that, we close the bootloader, go up to here, and go into our core or main C in the application. Now we need to modify the Now, first of all, let's implement those little things we did in this, primarily the print redirect and the blinking LED. So let's copy this, which we already did. That is the print redirect. We will copy that over in our application so we can print in the application. We will also copy that print there into our application. That should go down here, but we will call this application, and then we will do our whole loop down here. Let's copy that and do that. It needs to go here. So we now have exactly the same functionality, and if we are running this now, and it should come up and complain because it's the first time we are running our application, but that's okay. We just enable our serial wire viewer, which we're not actually using at the moment, and there is a mistake. Of course, I didn't in the application, I didn't enable the LED pin. So let's go into the CubeMX. I need a faster machine. Or a faster IDE, that's unfortunately. So let's set this one to output. Let's call it LED. Let's go into GPIO and set the LED as default high and GPIO mode open drain. And let's generate the code. Now, I'm sure that during this video I am going to make the mistake. It's very hard to edit two projects at the same time, and I am going to end up updating the wrong one. Notice up here in the header, you can see that this is the application. Right now, if we build the application, we should get away with that, and it is running. So let's try to run that. There we go. So now it's running the application. Put one more dash in there. So now we have the possibility of running the application. Let's try to flash that. There, application, tick, tick, tick. Or we can switch to the bootloader and run the bootloader. There. But at the moment they're occupying the same memory space. So here we need to relocate the application to a higher address. So on the application side, let's go in and edit the linker script for the application. First of all, let me do the E stack equals B flag, and let's call this the B flag, and -4. Then let's down here, let's set the flash to 1 instead of, so 80010000 and 448 kilobyte. Let's try to build the project. Let's close this one so we don't make, oh fuck, that was the wrong one. Excuse my language. I'm probably going to be banned from YouTube now, but here we go. That is our application. So we can see we now have starting at this address. And is this correct? End address. Okay. Give me a second. I am going to fire up a calculator and do this offline. No, I'm not. I'm going to fire up the application and do it right now. So let's go back in here and set this back to 0 and set this to 512. That's how it was before. So let's try to build this project. Application, am I actually doing the right thing? Launching. Don't understand why this sometimes updates, sometimes doesn't update. It's a bug in Eclipse, I'm sure, but it's a extremely irritating bug. What are we at? We are at almost half an hour already. We haven't really gotten around to anything serious yet. Generate code. Okay, it updated so we're back. So the last address should be 7FFFF. So if we take if we fire up a calculator and our starting address is, so first of all we have 512. We use 64, that is 448. So now let's start with hexadecimal 8000000. That is the start address down here. We need to add 64 kilo to that. So if we go to decimal and we add 64, clear, hexadecimal 8000000. Switch over to decimal. We add, it's not my day, hexadecimal 8000000. We go to decimal. We add 64 multiplied by 1024. We end up with 8010000. So if we go in here in the linker script again and we set the origin to 8010000, we will now have a problem if we are building that we're actually ending up way past what the processor is capable of. So we need to set this to 448. Save that, go to the main and try to project build. And let's try to run that. It works. So now I don't know why this one is not updating correctly, but I think I'm okay now. But the interesting part here is, well, we haven't really relocated it yet. There is one thing more we need to do. So we need to remember this address, which is our starting address of this application, and we need to tell the source code in here that we want to use a different address. If we look down here, you can see that we can define we can set this one. We will define this, and then we can actually set our flash base. So define flash base, no, to the address that we put in there. So now let's try to run this. It's the bootloader is flashing. I am doing this. Oh, you are kidding me. I did this again. Unbelievable. I knew that was going to happen. Have I been editing that bootloader application? Bootloader application, but this one is not the one I need to update. It is up here under application, source, this one, system. I need to set this, and I need to define flash base there. Now it's 48 and the end address is correct. Let's try to build this first of all. Build project, and let's try to flash the project. It runs the application and check. But now I should be able to demonstrate something interesting. If I reset the board, nothing is actually happening if I physically reset the board, and that is because this has now been loaded into a different address. If I go back, if I flash this again, it will run, but it will not run after a reset because it will actually try to execute the bootloader. Let's try for fun. Let's try to flash the bootloader as well. So we go in here, the bootloader, that should flash. There. And if I now physically reset, it will start the bootloader again. Actually, I think that if we now flash the application, it should run the application because this is called through the debugger. And if I reset it, I would expect it to run the bootloader. It does. So there you see, now we have the application loaded at, the bootloader is loaded at the, let's go over here. The bootloader is loaded at the beginning of the flash. Takes 64 kilobyte. It only uses 34 kilobyte, but it is loaded there. But the application is now actually loaded at a higher address. We can execute it through CubeIDE and the debugger because it forces the debugger, tells the MCU where to start, and it needs to start at this address. And it can run the application, but if we reset, it will end up back in the bootloader because the bootloader is the default. So what is left now to make this work? There is two things left. We should, or let me test another thing. Let's look over here. It actually doesn't come up. Let's see if I did something wrong. I'm just messing with the wiring. There. So this is a firmware update, so that is the bootloader. We should see now if I actually execute the application from in here, that should change. The application, which is a virtual COM port. So we can toggle the COM port. If it's in bootloader mode, it will show up as a DFU device firmware update. If it is in application mode, it will show up as a virtual COM port. So what is needed now is the interaction between the bootloader and the application. So let's start with seeing in the bootloader. First of all, we need a couple of defines. We need a a boot flag defined. We can do that. Actually, I should include, since I'm using printf DIOH, we should do a private define, which is our DFU flag, and I need my I need a couple of variables. I need not the E stack, but the B flag, and we have a variable down here. Now let's go down in the beginning of the code. Where are we? Hang on, I am seeing I'm not missing something. We need a few more things. Actually, we need a couple of functions, a jump to application address, and I am going to copy this code from another place. So if we are looking at down in the beginning, when we come into main, we have not initialized the clock or anything. So this check needs to be done, just verifying we are in the bootloader up here. So basically we set the boot flag equals the address of B flag. We check whether that is the dead beef application, and then we will jump. So we need this DFU default application. So let's remember that our application starts at 801.1.0.0.0.0. So if we go into our bootloader and go into our cube IDE, there is one change we need to make in here, just to have that address well defined. I need to take up singing lessons so I can entertain you while this is loading. Anyway, let's go down to the USB device, and we have the configuration of this. Let's world firmware update. I don't want that. Firmware update, and over here on the setting you will see that you have a default app address, and we need to change this default address to that, which is where we are going. We also need to change this one later, but I'll do that later. It's not relevant right now because we're not actually going to test the DFU today. We might do that later. There we go. So if that is not set, so if we are executing now, we are executing our bootloader, it should actually jump up to our application. Let's try that. There was an error. What is that? P function. I defined that, didn't I? Oh, I need to, yeah, okay, I need a type def for that. Private type def there. So we are defining it's a pointer to, let's see if we can build now. So now the bootloader should be loading, and then it should jump straight up to the application, and we should never see this stuff down here. So let's try if that works. So we're running the bootloader, but it runs the application. So now we have the bootloader actually jumping up straight up to the application, and the virtual COM port initializes immediately. Now let's make a few more changes so we can actually toggle between them, just to show you how that works. So let's go into the bootloader. The bootloader STM32 Cube MX. Where are we time-wise? Okay, still got a little bit of time, but it is getting too long. I'm not going to implement DFU today. So we actually, on this board, we have a input. We can do an interrupt down here, and we could call that button. And if I am not mistaken, we need to first of all enable the interrupt, which would be this one, and we need to set the GPIO to wrong button, by the way. Reset state. It should be this one. There. No. How is it possible for me to do it wrong 3 times in a go? It is PA0 that button is on. So there, enter user label button, and that button in here should be, well, we can try both the ways, and I think it needs to be pulled up if I'm not mistaken, because it's short to 0. We could go in and look, but I can't be bothered. I think it'll work. Now, in the main code, in the code of this, we need to add an interrupt, a callback for that. So if we get this interrupt, we're just going to reset. So by default, this will go in to it will jump to the application unless this boot flag is set. If that's set, it will run the bootloader. But this is pretty much all we need in the bootloader. Let's compile and flash this bootloader. It will go into the application because it's running the bootloader, and then jump straight up to the application, and it will start the virtual COM port. Now let's start to look at the application to make a few tunes. So let me close that, not to get confused. That it helps if we do it that way. We need to make a change in here in the application. We need to add that button as well. Here we go. So let's do it right this time. There, we set that one to interrupt, and we call it button. Not that, we will deal with that later, but we will pull it up and interrupt. Okay, so we need to enable the interrupt as well, which is that one. So I think that's all. Project, generate code. So now the big question is, how do we actually execute that bootloader? That means we need to set that boot flag, and we need to ensure that it and call a reset and set that boot flag. So in the application, that is actually quite easy. First of all, we need our boot flag defined that actually triggers. We need basically I'm doing copy. We need a couple of variables there. I didn't get that proper. Copy, paste. So basically this was the B flag, not the E stack. B flag, but the other one is correct. And then down in the beginning of our code, main, where do we do this? Oh, we can actually just do it like this. We'll do our callback for the button. We don't need to do anything, but where is that? We can do it here. So if the button is being pressed, okay, I'll do a time count here. So if it's being, what is pin state? If it is reset, that means get 0. And if it's released, okay, if it's been pushed for more than, we need that push count defined as a variable. So let's do that up under variable. We need the push count. I don't know if that CNT is being used. Then we will set our DFU boot flag. Where is, we need to set that. I think I'm missing that actually. So I will steal that instead from our bootloader because we had it over there. So if we go over to the call source main C, I need to execute this as well. We need this line, but we don't need to do anything about it in this one. So we'll just go down here. We will set our boot flag to the B flag. I did define that, right? Yes, I did. I'm sure I did. So that's pretty much it. If we press the button and hold it for more than a second and release it, then we should actually get into the bootloader. Let's see if this works. So run the application there. Run the application. Now I'll press the user button for a second. Let go. And we are into the bootloader. Now in the bootloader, if I just press, it should now go back. That is not working. So my button press in the bootloader is not working. But if I reset the process, we are back in there. So we only have one thing left, and that is that the button press is not working in the bootloader. So let's go down. That's the application. That is the bootloader. Let's run the verify the okay. I need to, I could actually, okay. So we have the button defined there. The button is an external interrupt in our GPIO, or did we enable the interrupt? No, we didn't. Well, that would explain a thing or two. Let's look at the GPIO 0. It is pulled up and it should be fine. So I just forgot to enable the interrupt. So let's generate the code. And let's briefly look at the code. So we just reset. There's nothing else to be done, and normally it will boot up. Okay, let's try to execute that. Now, it should actually end up in the application because that's it. When the bootloader is running, it will jump straight up to the application. But if we press the user button for 1 second, there, it will go into the bootloader. While we're at here, let's look at the USB. So now we are in a firmware update mode. If we click the button in here, it goes straight into the application and becomes a COM port. If I click and hold for 1 second, oh, it goes into the bootloader. So that's about it. This video is getting long enough. We created 2 applications, a bootloader, which, let me find it, which we are actually using 64 kilobyte of memory for that bootloader, but we could easily half that down to 32 kilobytes, so we could make this 32 kilobyte and the application give that application that extra 32 kilobyte. But on the other hand, we are not that short of memory, because if we look at the actual application, you can see that we still have 413 kilobyte of free memory in here, and if I am not mistaken, we actually never enable the optimization for that. So if we optimize this, we will have even more. Build project, we never optimize that. And let's execute. This one should drop. Oh, let's verify that it's still working. So click and hold and release bootloader, firmware update, reset, and we are back in the application. So it's as simple as that. We have created a bootloader, we have created an application, we have provided means of jumping between the bootloader, our homemade bootloader, and the application. Now in a future video, I won't promise this will be the next one, I will actually implement the device firmware update down in the bootloader. It involves essentially, in the app there's a DFU interface, and if you look at the DFU interface, you can see that there are a lot of functions down here that are not implemented. We'll need to implement those functions to actually update the flash from this DFU bootloader. So it is announcing itself as a DFU bootloader, but it isn't working at the moment. I'll do that in a future video. Meanwhile, if you learned anything from this video, please do like and subscribe. It takes some effort to make these videos, and I really appreciate the feedback. If there's something you don't like, please let me know in a comment below. That can help me improve these videos at a later date. I know this video is a little longer than it should be, but well, I wanted, it is a pretty big topic to cover, and I hope you learned something. As usual, please have a wonderful rest of the day.